Okay, let's unpack this. Have you ever looked up at the night sky and felt that pull?
That curiosity.
Right,
Yeah.
that intense curiosity about what's out there? Maybe you've even thought about getting a telescope. But then you dive into the research and, wow, suddenly you're swamped with technical terms, types, conflicting advice. It really can feel like navigating a cosmic maze. So today we're taking a deep dive into your sources on astronomical telescopes. We're aiming to cut through that overwhelming info overload.
Yeah, absolutely.
Because most people, I think, they hear telescope power and just think magnification, right? But that seems to be the biggest trap for beginners.
That's exactly right. And the sheer variety available now, I mean, from incredibly cheap ones to, well, very expensive instruments, it's staggering.
Right.
It's just so easy to get lost in the marketing noise. So our mission here in this deep dive is to give you some clear, impartial guidance. We'll distill the most important nuggets of knowledge from your materials so you can make an informed decision and, actually start enjoying the cosmos.
That's the goal.
We want to help you understand what's genuinely important and maybe what's just a distraction.
Perfect. So let's tackle that core misconception head on. What actually is a telescope?
Yeah.
And what truly makes it powerful beyond just making things look bigger?
Yeah.
Because I've definitely seen those ads promising, mind-boggling magnifications.
That's an excellent place to start. Really, it's where so many beginners get misled. At its core, a telescope is, it's deceptively simple.
Okay.
It makes distant things seem closer by doing two main things. First, it collects light, gathering much more than your eye can, to create a brighter image.
Brighter, okay.
And second, it magnifies that image to make it appear bigger. That's it. Every telescope, from basic binoculars right up to the Hubble Space Telescope, works on this principle.
Simple idea.
You have an objective, that's the main mirror or lens collecting and focusing the light, and then an eyepiece, which magnifies that focused image. It's like basically a reading glass for the focused light.
Huh, interesting analogy.
Yeah, in fact, your sources point out, if you take a shaving mirror, catch the moon's reflection in it, and then look at that reflection with a magnifying glass, you've essentially built a very basic telescope.
Wow, okay.
So the principle is simple, but, and this is crucial from your sources, telescopes need really precise manufacturing to work properly. You can't just slap them together.
Right, quality matters.
Definitely. Now, when we talk about powerful, it's not just magnification. Your sources lay out 4 basic factors that really define a telescope's performance.
Okay, what are they?
First, brightness. This is all about how vivid, faint stuff looks. Faint stars, nebulae, galaxies. And it's mostly about the clear size of that main lens or mirror its aperture. Bigger aperture means more light collected, brighter image. Simple physics.
Makes sense. Bigger bucket catches more rain?
Exactly. Second is resolution. That's the smallest detail you can actually distinguish, like fine lines in moon craters or maybe cloud bands on Jupiter.
Finer details.
Again, the larger the aperture, the higher the theoretical resolution. These first two, brightness and resolution, they're fundamental laws of physics tied to aperture.
Got it. So aperture is key.
It really is. Third is magnification, how much bigger things look. Now, this is variable. In theory, any telescope can give you any magnification if you use the right eyepiece.
Wait, any?
In theory, yes. But, and this is where it gets really interesting, and often counterintuitive more magnification means a dimmer image.
Oh, right, spreading the same light thinner.
Precisely. And it also magnifies every little wobble in the scope, the mount, even the turbulence in Earth's atmosphere, what astronomers call seeing.
So those crazy high numbers.
Exactly. Your sources strongly warn about ads claiming, say, 675 times magnification for a small, cheap scope. They aren't technically lying. But that magnification would be, and I quote, totally useless in practice. The image would be dim, blurry, and bouncing all over the place.
Okay, that's good to know.
Most scopes are realistically useful up to about, say, 50 or 60 times magnification for every inch of aperture.
Per inch, okay.
And anything much over 100x total magnification absolutely needs a rock-solid mount. Honestly. Even experienced observers rarely push magnification over 300x in practice.
It's way lower than some ads suggest.
Way lower. Finally, the fourth factor is Contrast. How well the telescope distinguishes between subtle shades of light and dark.
Like seeing faint details on a planet.
Exactly that. This is the most objective factor, and it really depends heavily on the overall optical quality. It's super important for planets. So yeah, while a bigger telescope is generally more powerful in terms of light gathering and resolution, you definitely shouldn't just buy the biggest one you see with the highest magnification number slapped on the box.
It really sounds like those ads are telling maybe half the story, if that.
At best, yeah.
Okay, so aperture is absolutely key, but not the only number. We see other specs on the box too. Beyond magnification, what else should we look at when comparing telescopes, and, why do they matter?
Right, good question. Beyond magnification, you'll often see two other main numbers. First is focal length.
Focal length?
This is simply the distance from the main lens or mirror to the point where it brings the light into sharp focus.
Like the focal length on a camera lens.
Similar concept, yeah. A longer focal length gives you higher magnification for any given eyepiece.
Ah, so that's good for planets and the moon, fine details.
Exactly. Moon, planets, splitting, double stars, perfect.
Yeah.
But the trade-off is that a longer focal length means a narrower field of view. You see a smaller patch of sky.
Less ideal for big star clusters or nebulae then.
Precisely. You might not fit the whole Pleiades cluster in, for example. And some telescopes use clever folded optics, so the physical tube is actually much shorter than the true focal length.
Sneaky. Okay, what's the second number?
The second is focal ratio, often written as an F number, like f6 or f8.
Like f-stops on a camera.
Exactly like f-stops. It's just the focal length divided by the aperture. So a scope with a 100mm aperture and 800mm focal length is f8.
Got it. So what does that tell us?
Well, shorter focal ratios, smaller f numbers like f4 or f5, mean a more compact scope generally, and a wider field of view. Great for sweeping the Milky Way, right?
Sounds good. But there's a catch.
There's always a catch. It's much harder technically to make a mirror or lens with a short focal ratio, a fast scope, perform perfectly.
Why is that?
Because the curves on the glass or mirror have to be much steeper, much more precisely figured to avoid optical distortions. Doing that well is expensive.
Oh, okay.
So this means, and this is a really practical tip from your sources, you are more likely to get good optical quality in a cheaper scope if it has a medium to long focal ratio, say f6 to f8, for a general purpose instrument.
So maybe don't chase the fastest scope on a tight budget.
Probably not, no. You're better off with a well-made f8 than a poorly made f5 at the same price.
Understanding those numbers really helps explain why telescopes look so different. So let's explore those designs, the actual types of telescopes. I still picture that long, thin tube. Is that the only kind? Or are there other big categories?
Oh, not at all. That classic long, thin tube you're thinking of is almost certainly a refractor.
Refractor. Uses lenses.
Uses only lenses, exactly. Galileo used an early version. And they can offer truly superb performance for their aperture size, especially with contrast on planets. Why? Because there's no central mirror blocking light like in some other designs.
No obstruction. Okay. Downsides.
Main one is something called false color or chromatic aberration. You might see a little fringe of purple or green around bright stars or the edge of the moon.
I think I've seen that in cheap binoculars.
Very possible. More expensive refractors, called apochromats or APOs, use special glass to pretty much eliminate this. But they get very costly, very quickly.
Costly.
Your sources mention a 16-inch APO lens alone could run $500,000.
Wow. Okay, maybe not for beginners.
Definitely not. Refractors also get very big, heavy, and expensive as the aperture increases. So for beginners, they make most sense in smaller sizes, maybe up to 4 inches or 100mm aperture. They're easy to use and versatile then.
Okay, what's next?
Next up, reflectors. These use only mirrors.
Like Isaac Newton's design.
Exactly, he formalized the design. And reflectors make up almost all big professional telescopes, including Hubble. Why? Because huge lenses are just impractical. They sag under their own weight above about 1 meter across.
Right.
The big advantages of reflectors, they do not suffer from that false color problem at all, and they're generally cheaper and lighter for the same aperture size compared to refractors.
Sounds good. Any common types?
The simplest is the Newtonian. Very common for amateurs, especially in a popular style called a Dobsonian. We'll get to those. Newtonians are simple to make well and can give absolutely stunning images.
Okay.
Then you have Cassegrains. These use a folded optical path, so the tube is much shorter and more compact for its focal length.
Easier to handle.
Often, yeah. And you usually look through the back end, which many find more comfortable than the side-mounted eyepiece on a Newtonian.
Any drawbacks to reflectors?
They do need occasional adjustment of the mirror alignment. That's called collimation. It sounds scary, but it's usually not too hard. And the mirror coatings might need refreshing after, many years of use.
Got it. And you mentioned ones that mix mirrors and lenses.
Ah, yes, the Catadioptrics. It's a mouthful, I know.
Yeah.
These use both mirrors and lenses, often based on the Cassegrain design. You've probably heard of Schmidt-Cassegrains, or SCTs, and Maksutovs.
Yeah, those names ring a bell. See them a lot online.
Very popular amateur scopes. Because they're compact for their aperture size, generally not too expensive, and they do most things pretty well, kind of a jack of all trades.
Okay, that fits.
They can offer a wider, flatter field of view than some pure reflectors, and the tube is often semi-sealed, which means the main mirror stays cleaner.
Yeah.
Well, they tend to be heavier than a similar-sized Newtonian reflector. Sometimes the field of view isn't as wide as a refractor or Newtonian. And a big one, especially for larger models, they can take quite a while to cool down to the outside air temperature.
Why is cooling important?
If the mirror is warmer than the air, it creates air currents inside the tube, which degrades the image, makes things look wavy or blurry. So cool down time can be a real factor.
Ah, patience is needed.
Indeed. Your sources also quickly mention spotting scopes. Those little scopes often used for birdwatching.
Yeah. Can you use those?
The advice is pretty strong. Generally avoid them for astronomy. Their optics often aren't quite good enough, the prisms inside can mess up the view of stars, and the magnification is usually too low.
Okay. Stick to dedicated astroscopes.
Right. And finally, there are specialist telescopes, like ones designed only for looking at the sun safely. The clear message for beginners is, start with a modest, easy-to-use, all-around telescope. Don't jump into a specialist scope until you know that's really what you want.
Get some experience first.
Exactly. Don't buy a fancy solar scope before you've even found the moon.
Makes sense. So, okay, you picked your telescope type.
Yeah.
But it needs something to sit on, right? A mount. It sounds like a great scope could be totally wasted on a shaky, cheap mount.
Oh, absolutely. You are spot on. The mount is just as vital, maybe even more vital sometimes, than the telescope tube itself for a good experience.
Why so critical?
Two main reasons. First, remember, stuff in the sky appears to move because the Earth is spinning, so the mount needs to track that motion smoothly.
Right, things drift out of view.
Quickly,
Yeah.
especially at higher magnification. Second, astronomical telescopes use much higher magnifications than, say, a camera on a tripod. That means any little vibration or jiggle gets amplified hugely in the eyepiece. A flimsy mount makes focusing impossible and viewing incredibly frustrating.
Nightmare. So what kinds of mounts are there?
Two main families. The simplest are alt-azimuth mounts, or alt-az.
Altitude and azimuth. Up, down, and left, right.
Exactly. They move just like a camera tripod. Up and down, altitude, and side to side, azimuth. Very intuitive to just push the scope around manually.
Sounds easy.
It is for finding things initially,
Yeah.
but tracking gets tricky at high power because you constantly have to nudge it in two directions, up, down, and left, right, to keep the object centered. It can be a bit jerky,
Oh, okay.
but a very popular, brilliant type of alt-az mount is used with those Dobsonian telescopes we mentioned.
Right, the Newtonian reflectors.
Yeah, a Dobsonian is basically a Newtonian tube sitting on a simple, sturdy, usually wooden alt-az base that rests on the ground, invented by John Dobson. It's a fantastic way to get a big aperture telescope relatively cheaply because the mount is so simple and effective.
Big bang for your buck visually.
Huge bang for your buck. And some alt-az mounts, including some Dobsonians, now come with Goto electronics, motors, and a computer that can find and track objects for you.
Okay, sounds high-tech. What's the other main type?
The other family is equatorial mounts. These look a bit more complex.
How do they work?
They're designed so one of their two axes can be aligned perfectly parallel to the Earth's axis of rotation, pointing towards the North Star, basically.
Why?
Because then, to track any object in the sky as the Earth turns, you only need to move the telescope around that one single axis at a constant speed.
Ah, so it matches the Earth's rotation.
Precisely. This is absolutely fantastic for keeping objects centered for long views and essential for long exposure astrophotography.
Makes sense for pictures.
Many have a built-in motor, like a clock drive, to do this tracking automatically once you find your target. And even manual ones make finding things easier using coordinate dials called setting circles.
Sounds superior then.
For tracking and finding, yes. But they can seem weird to use at first because the scope moves in diagonals, not simple up, down, left, right relative to the ground.
Takes getting used to.
It does.
Yeah.
And a good, stable equatorial mount needs to be quite heavy and robust, which makes it less portable. Plus, you have to do that alignment with the Earth's axis each time you set up, which takes a few minutes. So your sources generally say a good equatorial mount is not ideal for a total beginner who just wants quick, easy setup.
Portability and ease of use again.
Always coming back to that.
This deep dive has been incredibly detailed. Okay, so wrapping this section up.
Yeah.
If someone is just starting out, feeling that excitement, but also maybe that confusion, what are the most important, actionable things to consider when finally choosing that very first telescope?
Okay, crunch time. Your sources really hammer home 3 critical factors. First, and honestly, this might be the most critical advice of all, portability.
Portability.
Yes.
Yeah.
Choose a first telescope that is easily portable as a complete unit. Think about where you'll store it, how far you have to carry it, can you lift it easily?
Because
Because the biggest, most optically perfect telescope in the world will show you precisely nothing if it sits in the garage because it's too much hassle to set up.
the best telescope is the one you use.
That's the mantra. If it takes ages to assemble, then needs an hour to cool down, then takes ages to pack away,
Yeah.
you just won't use it often, especially on a weeknight.
Yeah, I can see that.
One author in your sources shared a personal story. They had a small, lightweight scope they used constantly. Then they got a much bigger, better, more complex scope. And it hardly ever got used because setup took hours. So unless you're lucky enough to have a permanent backyard observatory, tons of free time, and consistently perfect weather, avoid those really large refractors or reflectors as your first or only scope.
Start manageable. Okay, what's second?
Second is ease of use. You might actually be surprised how challenging it can be just to find things through a telescope at first, even the moon.
Really? The moon seems huge.
It is, but the field of view through a telescope, especially at higher power, can be tiny. Remember that long focal length giving a small field of view? That makes finding things harder, and they drift out of view faster.
Yeah.
And while GOTO systems sound great, push a button, find a galaxy, they often need a fiddly, time-consuming alignment procedure first, which can be really frustrating when you're just starting.
So what's easier for a beginner?
Your sources suggest a smallish telescope with a relatively short focal length for a wider field of view, and, crucially, a good finder. Like a simple red dot finder, it just projects a red dot where the scope is pointing, making aiming much easier. And put that on a simple, intuitive mount.
Keep it simple, basically.
Keep it simple to start. Finally, third factor, quality.
Build quality. Optics.
Both. The sources are emphatic. Mechanical and optical quality are paramount. Cheap, poorly made telescopes are just Durham. While the term used is a disappointing pain.
Okay.
And it's not just the lenses or mirrors. A focuser knob that's rough or wobbly, making it hard to get a sharp image. A mount that shakes every time you breathe near it. Those things can ruin the experience just as much as bad optics.
Frustrating.
Totally. So if you're on a tighter budget, the advice is clear. Prioritize basic mechanical and optical quality over electronic bells and whistles like GOTO.
Function over features.
Exactly. A simple, well-made achromatic refractor or a basic Newtonian reflector on a decent, simple Altaz mount will give you much better views and far more enjoyment for your money than some complex, feature-packed but shoddily built scope at the same price.
Good scope, good mount, simple eyepieces.
That's the recipe. That setup will perform way better than a poor telescope with super expensive premium eyepieces. Oh, and definitely forget anything that looks or feels like a toy. And avoid those cheap, unknown brands you might see in department stores. Stick to reputable astronomy brands.
Okay, so with all this fantastic information, quality, portability, ease of use, understanding the types, what's the actual roadmap? If someone's standing there ready to buy their first scope, what's your practical start here recommendation based on the sources?
Right, let's boil it down. And many beginners are really drawn to those Schmidt-Cassegrains on the GOTO mounts. They look impressive, computerized.
They do look the part.
They do, but your sources explicitly do not recommend these as a first telescope.
Really? Why not?
Remember, long focal length means a small field of view, harder to find things, and the complex mount needs that careful alignment. It can just be incredibly frustrating for a newcomer who wants to get observing quickly. They aren't really designed for that quick, casual look.
Okay, so what is recommended?
The strong recommendation is to start with a small, portable refractor on a simple alt-azimuth mount.
The long tube type, but smaller.
Exactly. Look for something with maybe 70mm to 100mm aperture, that's about 3 to 4 inches, and a relatively short focal length, maybe under 600mm or so.
Any brands?
Reputable brands like Skywatcher, Celestron, or Orion. They often have good starter packages in this range. This kind of scope makes a fantastic quick look, grab-and-go instrument.
Easy to take out for 20 minutes.
Exactly. And it will always be useful, even if you eventually upgrade to something much bigger. It remains your quick-look scope. If you happen to have a larger budget, your sources mention that a small setup from TeleVue is basically near perfect, but they are quite expensive.
Okay, so small refractor on a simple mount is option A. What if someone wants a bit more aperture right away? Maybe for fainter objects.
Good question. If you want more light-gathering power from the outset, especially if you're really keen on visually seeing fainter deep-sky objects like galaxies and nebulae, then a quality small to medium-sized Dobsonian reflector is an excellent choice.
The Newtonian on the simple ground board.
That's the one. Maybe something in the 4.5-inch to 10-inch aperture range. Again, brands like Skywatcher make highly regarded Dobsonians that offer amazing views for the money.
Big aperture, simple system.
That's the beauty of the Dobsonian. But crucial point for a beginner, avoid the GOTO versions of Dobsonians to start with.
Stick with the manual push-to kind.
Yes. Learn to